Okay, unfortunately, I had a computer crash after I left the class, and so I'm going to try to redo the problem that I was asked to do before. Here are the notes that have been posted, the PDF file. I'd like to point out that some of the variables that are being used in this diagram are different than the variables that I used in class. But they're similar, and so what I'm going to do is, rather than try to recreate what was done there, I'm just going to use these variables, and you can use this as another example of the correct free body diagrams if you use different variables. So rather than go through that again, we'll start at this point, and I'll show you how to do these other things that you were asking. So basically, from the free body diagram, I'm going to write these equations. So just like in class I had 4 equations, I'm going to have 4 equations again. I'm going to type them in as quickly as possible. I have the equations typed in. I believe I've typed them without making any mistakes. I execute those, and now what I'm going to do is solve them, the equations for the 4 variables. I'm going to give it a name. I'm going to call it transfer function, but we know that it's not exactly the transfer function. And the reason it's not, I'm going to close this window of the notes down. I don't think we need these anymore. We have the equations typed in. So I have the transfer function, with the exception that the transfer function should be dividing by the input, which this has not done, but it's close. In the class we had interest in the angle theta, so I'm going to just simply cut and paste that from the values. I'm going to give it a name. I'm going to say it's the theta transfer function. So that's my theta transfer function. Just to keep things simple, let's come up with some numbers. I have no idea what we set them to be in the class, so I'm just going to make up a few more. The numbers really don't make much difference. Okay, I need the R's. Okay, almost there. Okay, so I have a transfer function. What I'm going to do is what I did earlier. I'm going to find the denominator of the transfer function. I'm going to set that denominator, set the denominator equal to 0, and then I'm going to solve it for S. So there are 4 S's because it's 4th order. The time constant is 1 divided by 0.00686. So that's the, mistyped it. That's the time constant. The 2 frequencies would be 0.653 radians per second and 2.49 radians per second. So we've covered all of that before. Suppose we're looking for the steady state value when f is a sinusoid of 5 sine of 20, and 20 will be radians per second. Okay, so step one, what you do is you replace the, you take the transfer function, so I'm going to divide by the f, and I'm going to replace all s's with omega, which will be the forcing frequency times the imaginary number. So I'm going to do this in a fancy way. This means substitute, and so what I want to do is replace every s with, and I hit a minus and a greater than sign. S is 20 times the imaginary number. And so that is my first step. The F magnitude is 5, so I'm going to also substitute in F is 5. So there we go. And then I'm looking for the magnitude, which in Mathematica is the absolute value. So I'm going to ask for the absolute value of step 1, and so that would be the magnitude. So if you excite this with a frequency of 20 radians per second, you're going to get a magnitude of a very small magnitude. So it would be a bunch of zeros with 2, sine and cosine of 20. If you change the frequency, if you lower the frequency, so we'll make it relatively small, then your magnitude is going to be a little bit more. So in this case, the peak to peak distance would be looks like about 2.5, a little more than 2.5 on the sine wave, on the output. If you went even slower, so the frequency would be even lower frequency, the amplitude would be, well, actually I expected it to be larger, but but as the frequencies go up, the amplitude goes down. Okay, so you also want the angle. The angle of this, if I can get the, let's see, the chart back up. So to find the angle, what you want to do is, plot this. This is what the angle means. You plot the real part versus the imaginary part, and then you find the angle measured counterclockwise from the real axis. So for example, if the frequency in this particular case, let's go back over here, the frequency was 20, then we'll look at this, okay. With this frequency, the imaginary term is very, very small. Might as well call that 0. Well, this is a bad one. Let's take a smaller frequency, 0.01. Okay, this is a little bit better. The imaginary part is practically 0, and it's negative. So I'm gonna exaggerate it a little bit. Basically, I'm plotting that vector. So the imaginary part is a minus term. So, and it's really, 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 really small, but I'm going to exaggerate it. So it'd be a negative value. And then the real part is 1.25, positive. So this is a 1.25 here. This guy right here really should be 0.0009. But obviously I'm exaggerating that. And so I'm going to draw the vector, so it starts here and goes there, right there. And so what you want is this angle right there, which is a minus angle. So to do that, what I'm going to do is come back over here to Mathematica, and I'm just going to ask, it's probably easiest to do it with a calculator, but I'm going to use the arctan function. And usually when you do an arctan, and I'm going to give two variables, the two variables are vertical, comma, horizontal, but Mathematica uses everything in alphabetical order. So it's going to take the x component, comma, and then the y component. So it's basically backwards from what you would expect. But anyway, so you just basically you're going to take the inverse tangent. Okay, so in this particular case, Mathematica requires the horizontal piece first, and then it's going to ask for the vertical piece, which is a negative 0.000937. And this angle is going to be in radians. If you want it converted into degrees, you just divide by degrees, or degree, and that'll get you in, an angle in degrees. So the phase angle is a negative 0.04 degrees. That's how you do the phase angle. If you change the frequency, so for example, if you change the frequency, the numbers change, the plot changes a little bit, and the inverse tangent changes. So that's how you would find the phase angle.